Alright, guys. It says what force is required to accelerate a 3 kilogram buggy from rest to 5 meters per second in 4 seconds. So the first thing you have to do with this is find the acceleration. We're going to do A equals VF minus VI over time. This is always is a very long time.
Like through physics, will that?
It's we're gonna change it up some for circles, but it's a pretty standard formula. It's an easy formula. Nothing I ever do is good enough. All right, so my VF is 5. My initial, I'm assuming it's from rest, so I'm gonna put 0. I'm gonna divide it by my 4 seconds. Ends up being 5 divided by 4 is 1.25 meters per second squared. Okay, now that I have that acceleration, I can solve for the force.
So you're going to do the acceleration for the mass?
Mm-hmm. F equals ma. 3 kilograms times 1.25 is going to give me a force of what? Should be 3.75, I believe.
Yeah.
And because it's a force, we have to put it in newtons. Any questions over that? Pretty easy. The second one's a little bit of a step up just because the numbers are bigger.
I don't like this.
Okay.
Second one's not fun.
Second one's not fun? Is it just...
It's the times 10 to the 6th power. That's what really bothers me.
Okay, let me grab my calculator.
Want to use this one? I want to use my phone.
Keep it together. Keep it together. We're okay.
I forgot my.
Alright. So it says Saturn V's initial mass was 2.8 times 10 to the 6th kilogram, and it reached a final velocity of 11,168.9 meters per second in 112 minutes. What force was produced? I know that my velocity is in meters per second, so first thing I need to do is get my time into seconds. So 112 minutes times 60 seconds is 6,720 seconds.
Oh, no, not this.
Not this.
Not that.
It's okay, that's the only converting we have to do. Now we're going to find that acceleration.
Did you do A equals?
Uh-huh. So we're at 1.7 meters per second squared. Now it's asking again for that force, so I am not done yet. So we're going to do force is equal to that mass times the acceleration.
I think that should be a regular number.
I'll show you.
I like that.
1.7. So to plug that into the calculator, we're going to zoom out a little bit. Okay. Is that better? I'm going to do 2.8. Now that times 10 to the 6th power. If I hit my blue second and my comma button, it gives me that little E. That's that times 10. So I can just put 6.
Could we just put times 10?
You could, but this is a lot easier for me. And it gives it to me. Okay, so then I'm going to do times 1.7. That's my answer. 1, 2, 3. 4,076,100,000. You could also do 4.76 times 10 to the 2, 3, 4, 5, 6. Newtons. Yeah, but then I have to remember to change it back. Any questions about that?
Does that say 2.8
Yeah.
So
No, 2.8 times 10 to the 6, that E is that times 10,
Oh.
times 1.7.
So we can't just say 4 million.
Oh, you can totally say that. I just didn't like to write all the zeros. All right. Newton's third law, to me, is the easiest one.
You have the repair.
So we're going to find Newton's third law. For every action, there is an equal and opposite reaction. That is his third law. So again, for every action, there's a reaction. The forces are equal in magnitude, but they act in opposite directions. So if you have object A and you have a force of object A acting on B. So we would label this force of A on B. And we're going to put that little symbol above it to show that's a vector force. It's kind of like if you split like an arrow in half horizontally. Force of A on B. It just happens to spell fab.
Force on A and B?
Force of A on B.
Oh, force of A.
And then you have object B. That's applying a force of object B on A.
Is it just backwards now?
Equal and opposite.
Yes.
So what you end up is you end up with an equation like this. So why is it negative? So our negative there shows an opposite direction. All right, let's start again. So the law of action and reaction. That's what we're talking about. Says that in every interaction, forces occur in pairs. Law. It's cursive. Law of action and reaction. We good? All right, so I have a wall. That's my wall. Obviously, it's a wall. And I have my person, and they are on roller skates. Maybe they're rollerblades. I put an extra wheel in there. It's rollerblades now. Okay. And they're going to push off from this wall. So when they push on the wall, they have their force going into the wall. What is the wall doing back? It's technically pushing. Now,
Scientifically.
why doesn't the wall move?
It's friction.
Oh, close to friction. It starts with an I. We learned about it.
Fiction.
Inertia.
Oh, sorry. That doesn't even make sense. Oh.
Inertia.
Induction.
And now you're just bringing in middle school things. Inertia. You have to overcome that wall's inertia. You're probably not going to. It's attached to something. It would be really bad. You'd Hulk smash that wall. Would not be good. What's going to happen to the person?
They're gonna squish.
They're going to slide forward. I drew a curly arrow so you could see the motion, obviously. It's not going to go in that motion. They're just going to back off of that wall. Those are your force pairs. They're equal, they're opposite, but only one thing's moving. Okay, when a bug hits my windshield and I'm going 60 miles an hour down I-10, yeah, what happens to the little bugger? he gets dead, right? Hopefully. But my car is fine. Why?
Because there's mass go up.
Masses are different. The forces are the same, but the bug's body cannot withstand that force. Okay, so like if y'all ever watch Mythbusters on your own, when they would see like, oh, could you survive if you jumped off a 10-foot cliff but you dropped a hammer before to break the water tension? Like that was a cool one. I'll have to bring it up. Maybe I'll find that one for the warm up tomorrow. No. Well, I'm not gonna ruin the surprise. Don't do that. So, but they would put force reactions, measurement things on the dummy that they would throw to measure the force, because your body can only withstand a certain amount of forces before you either break something or die. And so that's how they would measure to see if it was survivable or not. I'll find a clip. All right. Now we have 3 different scenarios. So we have a rocket. We have a force upward from the chemical reactions going on, all those little combustion reactions, right, from chemistry. Where's the rocket? What? I know it's not as good as my rocket. I drew in some of your warm-ups, but it's still a rocket. I mean, mine was beautiful. Actually, the buggy took me forever. Buggy.
Drew that?
Buggy.
That's a shopping cart.
Buggy.
Where? I've never heard it called a blue
It looks like some buggy. I was thinking like a
Or troll.
like a punch buggy.
I mean, some people call them troll. It's a buggy, but it's a shopping cart. Whatever you want to call it.
That's
This.
a shopping cart.
Yeah.
I was thinking about the cars.
Welcome to class, man.
No, I thought you were talking about the rocket. I was like, that's
We
a
were
rocket.
we were talking about
You
the.
said that was
Hold on.
That's a shopping cart.
Hold on. Let's just, you know what? We're just gonna get it out of the way here. Here we go. I drew these warm-ups today, right? So some of them have a buggy on them. Some of them have a small buggy and a planet. Some of them have a rocket. That's Saturn V.
Oh.
That's a good rocket. Oh, I was wondering. I don't have a shopping cart. I got a rocket.
Anyways, I guess, yeah. Anybody needs to see evidence of my ADD? Here it is. So we have a rocket and it has a force upwards. And then we have a force downwards being produced as the reactants, as the products from that chemical reaction, not the reactions. The products are being pushed out and ejected. It's usually in the form of gases. You're also going to have gravity, assuming you're still in Earth's atmosphere, pushing down on you as well. Which is why you need so much forward thrust. That's why our forward force was so high for Saturn V, because you need a lot to escape all the gravity and the pressure and the air resistance and all that good stuff. All right, we have footballs and a foot. And the foot is applying a forward force on the ball. And the ball is applying a backwards force on the foot. Which is why you can feel the impact when you kick that ball. And if you kick it super hard, sometimes it actually will hurt your foot if you're kicking it wrong. I'm not athletic, so I don't know the whole dynamics there, but I know I can hurt myself doing it. This next one, we have a lovely breakfast laid out. So my breakfast is producing a force downward in the form of what?
Mass.
Keep going, not mass, starts with a W?
Wait.
Weight. That breakfast is producing a force downward in the form of weight. The table is producing a force upwards.